the lower bound for the element distinctness problem. I will first define the problem. The element distinction problem. Uh, we have an input of n elements, a1, a2, until an, and the output of this uh, problem should be yes if all elements are distinct. That is, there is no I and j with I different of j, such as ai is equal to aj. If any of the elements are equal to each other, then the answer is no. So that's it. We have only two answers, yes or no. And it is if all the elements are distinct. We're at the decision tree model. And in decision tree model, we have input a sequence of numbers, and they go in at the root. And the program is a tree, is a label tree, like this one. And each non-leaf node has a comparison of two elements, and each edge of the tree corresponds to a different result of that comparison. So, and the leaf nodes are labeled by the output of the algorithm. The execution, how the execution goes. A given instance uh, do that comparison comparison between, like in this example, the element I is compared to the element J, and if it's less than equal, it goes to the way this path, and if it's greater, then it goes to this path. Uh, we already know that the lower bound on the decision tree model also apply to the lower bound of cooperation-based algorithm for the same problem. So, and we also already know that that if the tree has m leaf nodes, then the height of the tree, which corresponds to the number of comparison, the number of relations, is at least log of n. In a specific case, we know that if the number of leaf nodes uh, for the tree of the problem is at least n factorial, it implicates that the the lower bound is n log factorial. We know that already. I'm assuming that this is, I don't have to prove that because we already know. And the claims, the lower bound of the element distinct problem for comparison-based algorithms is n log n. How will we prove that? We prove it. To prove it, it's sufficient to show that on decision tree models, the problem has at least n factorial leaf nodes that are labeled yes. If it has at least n factorial leaf nodes, then we know that the lower bound is n log n. So let's prove that uh, it has at least n factorial distinct leaf nodes. How we do it? Let's do an overview of the proof. Uh, We proved that there are at least n factorial lead nodes on the decision tree model that are labeled yes. How we do that? We use a geometric interpretation of the instance of the problem, and we prove that the region of L is the leaf, and is the set of all instances of the problem that arrives to that leaf. And we prove that it's convex set, a convex region. We also prove that if an instance of the problem arrives at leaf L, which is labeled yes, any permutation, a non-trivial permutation of that instance will reach a distinct leaf N, which is also labeled yes, not the same leaf. Any permutation will arrive at a distant leaf. That is also labeled yes. So let's start by the geometric interpretation of the instance. Given an instance of the problem, the inputs are n numbers a1 to an. Let's interpret that each instance at a point in the n-dimensional space. The region of all these instances is the n-dimensional space itself. Let's take an example for n equal to 2. Each instance is a point in the 2D space. So here, A1 is X, A2 is Y, this is the point, and any instance of the problem will go in this plane. This is easy to generalize it for any multi space and any dimensional space. Uh, so let's continue with the geometric interpretation of the instance. Uh, let's let's execute uh, the instance using the decision model, the decision tree model. At time we execute one. This is a part, only a part of a partial part of the tree node, the decision tree. We do a comparison here and need to go to either this edge or this edge. The each edge and it compares two coordinates, the ith coordinate with the jth coordinate of that point. And when you do that, we split the region in two different regions. Um, I will go a little further so I can better explain this. The intuition behind this is um, all instances are points in the n-dimensional space. And this region, the n-dimensional space itself, is convex. At 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 each node, at each edge, let's say this edge, I will divide that space in two different regions. One region that acts, in this case, AI is uh, less than AJ, and another region which AI is greater or equal than AJ. And so I have to do. And if I do this successively until I get a, a rich a leaf node, it will still be convex. Why it's convex? The space is convex. If you divide, split this space, is still convex. So this is the intuition, geometric interpretation of diseases. And in the decision tree model, the we say that the region or, or the region of the instance, the set of all the instance that will lead to a specific uh, leaf node is a region that is convex. Let's prove it. Let's prove the convexity on on the region of the instance that reach the L node on decision tree. And the convexity of a region is it's the, by definition is if any point C between two arbitrary points A and B in that region, that point C is also in the region, like in a cube, the, the full cube, including its interior. Any point between the cube and any other point in the cube is also in the cube. This is a convex region. A sphere, the same way, the full sphere, with, including its interior, is convex because any point on this region, if I take any 2 points in this region, all points between them are still in the region. Uh, so let's take C, an arbitrary point between A and B. Uh, we need to prove that this point is also in the same region. And then if we prove that region is convex. Let's say that C is alpha A plus 1 minus alpha B. So with alpha being in the interval of 0 to 1. So C, in fact, is a point between the point A and B. Uh, let's say that A uh, per, belongs to the region of the node, the region of the instance that go to the that arrives at the leaf L, and B also is in the same region of the instance that goes to the leaf L. This and this implicates that C C belongs to the region, and so that the region is convex. Let's prove it. For A and B to belong to the region L, they if they in the decision tree model, if they belong to the same R of L, they must reach the same leaf node L. And for they to reach the same reach leaf node L, they have to perform the same path. They have to follow the same edge um, from the root until the leaf. Otherwise, they will not reach the same leaf node L. So Let's take just one of these uh, node, an edge, followed by an edge. And let's assume that both instance A and B go through that node. This is we can do this without losing any generalization. We can take this node as I and J, and the edge, and the edge is the less than. So if both instances go through that path, uh, and we know that they do because they both pertains of the same region, then A of I is A of I is less than A of J, and so are B. B of I is less than B of J. That if I multiply this for alpha and this for 1 minus alpha on both sides, which are positive numbers, both are positive numbers, uh, we and summing up this inequality, I get this inequality. It says uh, that alpha A, that says that simplifying C of I is less than C of J. That is, this implicates in this. That is, A being in R of L and B being R of L implicates that C is also in R of L, being C any point between A and B. And this proves that R of L is convex. Let's go to the follow proof. Um, we have to prove that there are main proof, which is that there are n leaf node label yes. The claim is any non-trivial permutation of an instance of the problem which arrive at leaf L label yes. Any non-trivial permutation of this instance must arrive at a leaf L prime, which is different from the leaf L, but also label yes. The proof will be done by contradiction. Imagine that A and B are in R of L, which is a convex region, and L is a yes leaf node. That are the conditions. B is a non-trivial permutation of A. We know that it's easy to, it's obvious that any permutation of an element can be done by successively doing permutation by pair. I, for example, first permutate two elements, and then I permutate more two elements, and and then I can reach any permutation, any possible permutation of an element by doing multiples permutation of two elements. So if I prove that any permutation of two elements uh, lead to different leaf nodes, then I prove that for any permutation, it for any permutation, it will lead to to a different node, leaf node. So it's sufficient to prove that any two permutations of I and G, or I and J for I different J, if I permutate element I with element J, uh, if I prove that this lead to two different leaf nodes, then I prove that any permutation that can be done by combining permutations two by two will also lead to different leaf nodes. Uh, the middle point, for proving this, I will take the middle point, C. Uh, A is an instance of problem, B is an instance of problem. A of B divided by 2 is the midpoint, C. And it's, we know that it's also in the region, in the same region, because the region is convex. So R, C is also in R of L. But if I compute the the coordinates ci of this point, all the other coordinates other than I and j are equal. Uh, but for ci and cj, uh, they are the middle point. For all the middle point, but as we want to permutate two elements, the other are equals. Only the I and the j elements are permuted between A and B. The other elements are equal. So the middle point, the coordinate Ci of the middle point is AI plus BI divided by 2. And that's equal to AI plus AJ, because AJ is equal to BI. I exchange the 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 two in the permutation, divided by 2. And Cj is Aj plus Bj divided by 2. But Bj is also Ai because I switched them. So Cj is equal to Aj plus Ai divided by 2. What I got here, Ci is equal to Cj. But they can't be equal, because otherwise it would not belong to R of L, because R of L is a leaf that is labeled yes. So all all the instances of the problem that go to that must have all distant elements. And as Cj is equal to Cy, this is not an yes, but it lead to a yes node. This cannot be true. So I proved by contradiction that any non-trivial uh, permutation of A will lead to a different leaf node, which is also labeled yes, because the elements of a permutation are still all different. And then, as a summary of this proof, we have proved that. As a summary, to summarize and to conclude, the decision tree model with n factorial leaves has uh, ha we know that the decision tree model with n factorial leaf node has the time complexity of n log n. The geometric interpretation of the region of the instance that goes that arrives at the leaf node L is convex for the decision tree model. For the decision tree model, for the problem, for the element distinctive problem, we know that any non-trivial permutation of an instance of the problem arrived at a distant leaf label also labeled as. We have proof of that. So how many how many non-trivial permutations of a distinct uh, input with any distinct elements, there's any factorial permutation. So this proves that, summarizing everything, we have proved that as we have at least any factorial, we have any factorial permutation uh, for for any instance of the problem that leads to yes, where that is that all the elements are distinct. So if there are any factorial permutations for any instance that that result to yes, there are at least n leaf nodes on the decision tree model, which leads to uh, uh, time complexity, a lower bound time complexity of at least n log n. That was what I wanted to show you. Thank you.